last time, I mean, many things I have covered. So once and have a quick of all those things so that you can go through it in details. I'm just reviewing all those things. Next, I'll see the other things. So initially, what we have seen these things, the pulse broadening. It is how to calculate this pulse broadening. We have seen this dispersion effect. Okay, just a minute. We have seen the in a fiber, if you launch some pulse shape will be broadened, right? And because of dispersion effect, and not necessary. I told you also, pulse shape can be narrow. It can be narrow also because of nonlinearity. For the timing, it is not being discussed here because it is the advanced stage of this. Maybe at the end of the fifth module, we'll discuss it to some extent. Nonlinearity, soliton, those things will be discussed. Yes, soliton is there. At the last module, we'll see it. That time we'll see it because of nonlinearity. In the spectral broadening will be there, not pulse broadening. Spectral broadening means many frequencies will be generated. So in that case, actual pulse will be very narrow. Right. So, but anyway, right now we are considering the pulse broadening effect because of dispersion, and that is because the group velocity is a function, group velocity function of wavelengths. Right. So the group delay we are calculating as a whole. I mean, there are several dispersion effect. I told you intermodal dispersion, intramodal dispersion. Intramodal, it is in case of SN fiber, and in case of multimode fiber, intermodal dispersion is here. In fact, intramodal also it will be of two types. It can be material dispersion, it can be waveguide dispersions, right? And how can you calculate this dispersion? Actually, it will result the pulse broadening. So we are interested in how much pulse spread will be there because of this dispersion effect. To calculate this one, we have to calculate the group delay. That is TG group delay. That is group velocity is VG. So 1 upon VG, that is the group delay. That is TG upon TG. That is a delay. So TG by L, delay per unit length. So that is from the definition of group velocity, where it is in terms of lambda. It is minus lambda square by 2 pi c d beta by d lambda. Right. This one we have seen it last times, and this, since it depends on the spectral width. So a source, it has some spectral width. So delay per unit wavelength, they have to calculate it next total spectral width. So that is actually the pulse spread. Is this one tau g. This tau g actually we are tau g here, tau g, and this tau g, it is this one we have calculated. But here you see it is difficult to distinguish the material dispersion, waveguide dispersion, other dispersion. So we have calculated this dispersion effect separately. When the pulse brought in due to this dispersion separately, say for material dispersion, how much pulse spread will be there? That can be calculated. You see in the fashion that the beta is a function of when refractive index. Actually, refractive index, it is varying nonlinearly with lambda, right? So that is actual cause for this material dispersion. And since it depends upon the spectral weight, so LED, it will provide more material dispersion compared to laser source. How to calculate this pulse spread due to material dispersion? So in this case, group delay, we know we have just now seen basic differential is in terms of lambda. It is minus lambda square by 2 pi c d beta by d lambda. So beta actually to 2 pi by lambda times n, right? And the refractive index. So beta equal to 2 pi by lambda times n. So that is the case. So if you substitute the beta and if you just simplify it, you will get this one. There is a group delay due to material dispersion T mat, right, over a length L. And the pulse spread, this is a delay. And pulse spread will be in the same way. You have to consider the whole spectral width of the source. That means delay per unit wavelength multiplied by the spectral width. That's what it is here, per unit wavelength times the total spectral width. So if you just do it and simplify it, you will get the important expressions of this material dispersion in these ones, right? This is lambda d2n upon d. This factor generally is provided for if you want to calculate this one for a particular material, generally it is provided. And so if you know the delta lambda and other factors, you can calculate the amount of pulse rate. And we have seen if you plot this material dispersion versus lambda, it is 0 at certain wavelength, I mean at 2.1.27 microns. And for silicon oxide, if you glass fiber, if you consider, then at this particular the material dispersion will be 0. But it's very difficult to get a source at this particular wavelengths. Right. So always material dispersion will be there, would be there. But of course, it can be minimized with some other dispersion like waveguide dispersion. What is the reason for waveguide dispersion? We have seen this when light is launched within the fiber. Certain power is carried within the core, and certain power is carried within the clad. Right. And this core, I mean 80%, 20%. Right. And the refractive index is different. So obviously, there will be dispersion effect. Pulse broadening will result because of this refractive index variations. Group velocity will vary, and in that way you can have the pulse broadening. So how to calculate this one? Since material dispersion is inherent problems, if you want to calculate the waveguide dispersion, then you will not be sure whether it is due to waveguide dispersion or material dispersion. So to get the waveguide dispersion solely, then you see you have to consider the n should be independent of lambda. So we have expressed all the relations in terms of n2 where it is independent of lambda. Right. So that's what we have seen in this normalized population constant. It is expressed in terms of n2 as well as v also, v number also expressed in terms of n2. You see it is here Ka n1, and approximately it can be like these ones. So in the same way, from the definition of group velocity, group delay, it is L by C d beta by dk. So beta this time it is just now I've shown you earlier last class also. It is this one. So substituting this value, you'll get this. This is the expression for group delay due to waveguide dispersion, and this can also be explained in terms of V. If you substitute this K by V, so it will be same as this. Only K will be replaced by V. The parameters are generally given in terms of dV by d lambda 2, d2 V by d lambda 2. That's what it is there. So once you get this group delay, then you can find out the amount of pulse rate. The same way, per unit wavelength times total spectral width. So that is a spectral width. So if again you have to differentiate with respect to lambda. I told you how to calculate this with respect to lambda. dd lambda of this one will be there. dd lambda of this one. Right. With respect to lambda, so d2 Vv by d lambda 2 will be no. First, this one, this will be with respect to lambda, but so dV by d lambda by dV. In this way, you can write it. So d lambda by dV, you can calculate from these relations, right? Like something like this. This one, right? And once you substitute this one, then you will get it. d2 Vv by d lambda 2. This d by dv, you can write it in this way: dv by d lambda to d lambda by dv. So this one and dd lambda of this one, that will be as d2 Vv by d lambda 2. Right? This you will get it. So after simplifications, you'll get it L then to delta into N2 divided by C lambda into this factor into delta lambda. This factor will get it. It is nothing difficult at all. It's just simply using the differentiations, you can have it. So that is the waveguide dispersions. This can be compared with this. We'll see the comparison is here. How much contribution is due to waveguide dispersion, that can be compared. Okay, but the most important thing is you see with the with the knowledge of this material dispersion, Auger dispersion, we can design the dispersion shifted fiber. That is the most important things. Because you see, attenuation is minimum at 1550 nanometer. So, but in this case, material dispersion will be present. So material dispersion very difficult to eliminate because it's inherent case. But Auger dispersion, it depends upon the fiber parameters. So see, it can be controlled. So if you consider this material dispersion almost equal to the Auger dispersion, then the total dispersion effect will be minimum at certain wavelength, that is 1550 nanometers or 1.55 micron. So if that is the case, then it is called dispersion shifted fiber. That is the most important fiber, single mode fiber, right? And also another class of another type of fiber is there, which is widely used for wavelength division multiplexings or DWDM systems. These are the latest technology used in FiberPlex systems. FTTH probably has fiber to the homes. You have seen this FTTH. So in those cases, DWDM system is used. WDM, it is say up to 16 wavelengths, 8 to 16 wavelengths. More than that, it is DWDM systems. So more wavelengths are when more wavelengths are used. So in that case, you see, you need some region where net dispersion curves should be a minimum over certain wavelength regions, right? So here you see in this case, dispersion effect is minimum over certain wavelength regions, right? So if that is the case, then that is called dispersion flattened fiber. Dispersion flattened fiber. Dispersion flattened fiber. That is the case, right? Well, these are these these are material dispersion or Auger dispersion, and also we have seen this. Yes, anybody want to say anything? Anyone want to say anything? No. So next is the intermodal dispersion. That is in case of fiber, it is useful. Fiber, multimode fiber. Here the reason is this: fiber is no need of these things. The wave concept to group velocity. Simply here, if you consider the geometry, you can calculate the time difference or the pulse rate. All right. Here you see time difference will be occurring because of these the two extreme rays. One is the axial ray, and another is marginal ray. Marginal ray that is having maximum angles. Beyond this, beyond these things, that ray will not be trapped. That will be reflected out. That will not follow the total net pressure conditions at this point, right? Core clad interface. So how to calculate this? The time difference between this marginal axial ray. So from the geometry taken this triangle, if you just consider, this is a L1 axial direction L1, and this ray having some angles with the axis, that is L2, this path. So L2 minus L1, that will be the actually length difference, the delta L. And if you just consider the trigonometric relations, then L2 can be expressed in terms of L1 like this one. So with this L2 minus L1, you can have it L2 minus L1, right? That is L1 into delta, you can have it, right? And so delta T, the time difference, that will be delta L into N. Refractive index will be there within the mediums, right? Into C. S equal to Vt. S equal to Vt, but here S should be multiplied with the refractive index of the mediums, N1. So ultimately you are getting N1 delta L upon C. That is the maximum times taken by the marginal ray and the minimum time taken by the axial ray. This is marginal ray. This is the time taken by the axial ray. So the time difference, it is N1 delta L upon C. So in this way, you can calculate the time difference between these two, between the two extreme cases, and that will result the pulse broadening in SI fibers. This pulse broadening actually can be minimized in GI fibers. In that case, since this ray move fast, short distance, and this ray, marginal ray, will move longer distance. So you can consider the refractive index variation in this way, in such a way that this ray will move faster compared to this axial ray. Then they will arrive at the same instead of times. and that is happening in GI fibers. That's why in GI fiber bandwidth is more than the SI fiber, right? Because on the rays they will arrive almost at the same times. You see, the time difference will be very small, can be minimized by varying the refractive index. Because n equal to C by V, I told you. So so V equal to C by N. So when the refractive index is maximum, the velocity will be minimum. So for axial ray, distance is less. Distance is less. At the same time, refractive index is more. We have seen this in JFR, refractive index, the axis is more, so moment velocity will be less. And in this case, marginal ray, they are traveling longer distance, but since refractive index is less, so their less means velocity will be maximum, right? So more velocity will be there. That's why though they are traveling longer distance, but since the velocity is very high, so they will arrive at the same instrument times. So in this way, in case of GI fiber, you can minimize this time difference, and in turn, you can have high bandwidth fiber. That's why generally for metropolitan cities, GI fiber used. Generally, multimode fibers are there. So SI multimode fiber is avoided because their bandwidth is small, right, compared to GI fibers. SM fiber also can be used, but SM fiber, some other constraints are there, like you need only laser sources, and also right, otherwise power launching problem will be there, etc., etc. So many problems are there, right, in SM fiber. Advantages are there, disadvantages are also there, right. Also, we'll see when you use the coherent sources, some coherent noises are also there. Suppose in between fiber, you have seen some splices, connectors are there. So if you use the connectors or splices in case of single mode fiber, then some noises will be taken into account. That is because of coherent noise, speckle noise, etc., etc. So when you consider the sources, that time it will be clear. So this is the last class I'm quickly covered last time. So now again I have repeated so that you don't have any problems towards the quizzes or towards in some point of view. Okay, just a minute. I'm now to the next slide. Some design aspect of the single mode fiber. Just a minute, once again. This slide is visible. Harshvardhan, this slide is visible.
Yes, sir.
So here some design aspect of single mode fibers. Here you can see it here. Generally telecommunications for very long distances. Just a minute. These everything you can have it in the Kaisers, what I have discussed so far. So you see, for very long distance systems, single mode fibers are there. So how to design the single mode fibers, right? You see, with V number also we know it for V numbers. If it is less than V number, it is 2 pi by A times lambda, 2 pi by A divided by lambda times numerical aperture, right? And this V should be greater than equal to 2.40. Actually, it should be slightly less than 2.405, but the maximum limit is 2.405. So that is the condition for single mode fiber, right? And in single mode fiber, you have seen this the two types of dispersion effects: intermodal dispersion, material dispersions. I mean, intermodal dispersion, that is consisting of the two types: material dispersion and waveguide dispersions, right? So you see, I told you the material dispersion is very difficult to alter, but because inherent case, but it is possible to modify the waveguide dispersions, right, through the fiber parameters by using complicated index profiles. By using complicated index profiles, you can change the waveguide dispersion. So if you change the weaker dispersion in such a way which is almost equal to the material dispersion, then total dispersion effect will be minimum, right? So that's what it is. The target of designing of single mode fibers by changing the different index profiles. We can design the single mode fibers, right? And there are three different types of fibers are there based on the refractive index profiles. One is 1300 nanometer optimized fibers. The first one, you can see it. First one, this is 1300 nanometer optimized fibers. Second one is dispersion shifted fibers. Just now I've discussed dispersion shifted fibers. And the third one is dispersion flattened fibers. Right. These are actually used in telecommunication systems, telecommunication network, very long distance systems. Right. And this type of fibers can be designed by properly choosing the core and cladding refractive index configurations. Right. You see it here. In case of 1300 nanometer optimized fibers, it can be either matched cladding or can be depressed cladding. Right. In matched cladding, you can see it here. This is the core. This is clad. So cladding refractive index, it is constant. Right. Here. Generally in a fiber you have seen this one core, one clad, but now we'll see more than one clad can be there. One clad will be there. I mean, based on refractive indices. So that is the match cladding. When refractive index of the clad is near very after this core is constant, but here you see here here varying is there. Varying means not continuously varying. Immediately after the core is refractive index is one type, and after a certain distance again it will be a so cladding of different types. You see here delta 1 that is 0.25%, another it is 0.12%, right? So in this case, in case of depressed cladding, the cladding portion next to the core, cladding portion next to the core, with lower refractive index, lower refractive, if you see the delta, it is 0.25 and it is 0.12, right? And delta N1 into N1. So you see it here. It is lower refractive index compared to the outer cladding refractive index, right? So that is the depressed claddings. So material dispersion, we have seen this earlier. Seen this. It depends on the composition of the materials, where n is a function of lambda, and waveguide dispersion, it depends upon these different parameters of the fibers. So it can vary with the fiber parameters. So by shifting the dispersion to wavelengths, when we got dispersion to longer wavelengths, we can minimize the total dispersion, right, towards 0. So that will result that dispersion shifted fibers. Next ones. So it is 1300 nanometer optimized fibers. This is one type of fibers, 1300 nanometers, and another fiber is here. Here it is dispersion shifted fiber. In this case, you see a profile is something conventional step index fiber, step index profile. Another one is a triangular with annular rings, triangular with annular rings. So you can see it how the refractive index is varying in this way. This is the you see different delta 1, delta 2. This type of triangular profile is here in case of dispersion shifted fibers. Dispersion shifted fiber. So triangular with annular rings. Then you can have the dispersion shifted fibers. By refractive index, by properly choosing the refractive index fiber, you can minimize the dispersion effect at 1550 nanometers. Right. There will be another type of fibers based on this refractive index profile. that is dispersion flattened fiber. I told you where dispersion will be minimum, here dispersion minimum and at a particular wavelength, 15 nanometers. But in the third one, the dispersion is minimum over a certain range of wavelengths, and that is useful for dense wavelength division multiplexings. So in this case, very complicated profiles are there. You can see this is W profiles. You see W profiles, how different indices are there. So more than one clades are there, you can see it. Here is quadruple clad profiles, more complicated profiles are there. So with these profiles, you can design dispersion of flattened fibers. Dispersion flattened fibers. Right. So by properly varying the refractive index profiles, you can design 1300 nanometer optimized fibers or dispersion shifted fibers or dispersion flattened fiber. Right. These things are there. Three types of single mode fibers are there, and you can see their profiles in three-dimensional aspect. You see it here. This is the matched cladding. This is the matched cladding, and here the depressed cladding. You can see, and their three-dimensional view of refractive index variations. And in case of dispersion shifted fiber, you have seen this triangular with annular ring. You see, this is for dispersion shifted fiber, and much more complicated refractive index profile is there for dispersion flattened fiber. Right. So there are the three different types of single mode of fibers there. Well, next you see this is the step index fiber, but in the same way also you can calculate the GI fibers. GI fibers is very much complicated because here you have seen these some approximation methods are there, but here also you can calculate the pulse broadening, and in this case you have to consider the RMS pulse broadening in GI fibers, root mean square pulse broadenings. Well, I told you in GI fibers that intermodal dispersion can be minimized by varying the refractive index within the core. So at that time, I told you several times that the axial ray and the marginal ray, they will almost arrive at the same instant of times because of the different refractive index variations, in turn different velocity. Of the different velocities, right? Maximum velocity you can have it for marginal ray and minimum velocity for the axial ray. So axial ray moves shorter distance. So and marginal ray they travel longer distance. So they will arrive with the high velocities. So the thing is they will arrive almost same instant time. So pulse broadening will be nullified. But how to calculate this different dispersion effect in GI fiber? You see here also the techniques are there. I'm just mentioning the steps how to calculate it. The same way, same concept is used through group delay, but here RMS pulse width is considered. Here one method is there. So here RMS pulse is due to the sigma square intermodal plus sigma intermodal square. The first one is the pulse width from due to intermodal delay distortion, and this is the sigma due to due to within a mode the sigma intermodals. Within a mode the pulse width variations, this factor intramodal intermodals. And the sum of these two will provide you the total pulse rate, total pulse spread, right? And so individually, how to calculate this one, sigma intramodals and sigma intramodal and intermodal. Here see taking the average of the group delays. This is tau g square minus tau g average whole square. That will provide you the sigma intermodal. What is this average? Average means it is over the modal distributions, mode distributions, average. So if you consider say a particular parameter say A, that means it is sigma, the new m modes levels are new m's. So over all modes, P nu m's into A nu m by m's. For any factor, say it can be tau g square or it can be tau g, whatever is the case. So it is the power content in that particular mode multiplied by this this factor A nu m's by AM. M is the total number of modes. Total number of modes. Just a minute. Let me check it. Average of it. So A nu m's, that is for particular mode of order A nu m's. And this is the average value. Right, average value. So the average value, these ones. So group delay from the basic definitions, you know, group delay, that is L by C 1 upon Vg, that is L by C dB/1 dk. So from this you can calculate once you beta. So beta actually you have seen this GI with your WKB approximations. Beta a function of beta generate 2 pi by beta, you know, beta equal to 2 pi by lambda times n. But in this case, it will be 2 pi by lambda times nr. And nr, you know, in GI fiber, you know, it is n1, 1 minus 2 delta r by a equal to alpha equal to half. So these things are there. So if you all those things, if you consider and calculate the group delay, etc., with beta, etc., you will get big expressions. You'll get it. The expressions are given in Kaiser. You can see it, right? So in that way, you can calculate the intermodals through this average value of this group delay. And how to calculate this intramodal? For intramodal, this definition is used by some worker, researcher. That is sigma lambda. That is actually delta lambda by lambda square into lambda d tau g by d lambda square average. So if you calculate this one, then you can have these ones, right? And this expression, it is shown it here, lambda d tau g of these ones. This type of expressions you can have it after simplifications. So so from the group delay, you can calculate these ones, and by neglecting the higher order terms, you can have this one, these expressions. So once you get this one, then you can calculate this, the RMS pulse width due to intramodal dispersion in GI fiber. So once you get this intramodal and this pulse width and intermodal pulse width, then you can have the net RMS pulse width due to intramodal and intermodal dispersion effect. Some more thing about these things. Waveguide dispersion, we have seen this, it is of importance in single mode fiber, and it can be of same order of magnitude as the metal dispersions. You can compare it. I told you, you can compare how much, what is the contribution of waveguide dispersion compared to metal dispersions. You can see it here. With this, you can compare it. You see here the expressions you have seen last times. That is N2L delta lambda sigma lambda, this sigma lambda C lambda into this factor. That is the for waveguide dispersions, right? This factor, you see, this factor generally is plotted as a function of V. Say for fundamental mode, single mode fiber, you have to consider the fundamental mode. So you can see it here. So you see it. This is the values for different value of V, but it should be within 2.405. This is single mode. It is single mode. So you can have this is dV by dVV by dV, and this is d2VV by dV2V times. So if you know this one, then you can have an idea of how much waveguide dispersion will be there, and you can compare it with the metal dispersions, right? And this curve also, this indicates this dispersion shifted fiber. You can see it here. Metal dispersion, it is metal dispersion, it is somewhere it is 0 1.27, but that times other dispersion is present. So if you consider almost at this point 1550 1550 nanometer here, 1550 here, 1550 in this range where the metal dispersion and the Wave dispersion is minimized, then you can have the dispersion shifted fiber. Right. So these are the different things there. Okay. So till now your quiz will be there. So if you have any questions regarding these things, you can discuss, or otherwise I'll just give some introduction of the next modules. Anybody, if you have any questions, you can ask. Any questions from any topic for the quiz or for your knowledge? Any questions? Master Vardhan, any questions? Till now it will be your quiz.
No, sir. Sir, is it possible once can you summarize the concepts in a brief?
Brief for what? Which concept? Tell me. Which
Sir,
one?
the
Which lecture?
equation, sir, model equation part.
Which one?
Sir, that model equation part, sir. We were having Bessel's equation, that part.
Oh, acha, that part. Okay. You see, okay. Slide is not with me, but I'm telling you what we have done, right? What we have done in case of modal equations, mode optics. Why you have considered the mode optics? Because in single mode fiber, ray optics fails. First things, right? Ray optics fails. Why? That is because in the concept of ray optics is there when lambda, ray optics can be used if lambda tends to 0. But means if you consider the neglect finiteness of the wavelength of light, that is true for multimode fiber. Multimode dimension is quite large, and maybe it is I told you it can be 50 to 100, 50 to 200 microns. So suppose if it is 100 micron, if it is a core diameter, then lambda it is say 1 microns. Or you have seen this one 0.8 to 1.6 microns. So with respect to 100 microns, you can neglect the finiteness of the wavelengths. So in multimode fiber, you can use the ray optics, but for single mode fiber, you cannot use it because single mode fiber, the dimension is core diameter is also can be 2 to 10 microns. Suppose if you consider the 2 microns is the core diameter and lambda is say 1 micron or 0.8 microns. With respect to 2, we cannot consider 0.8 0 or like that, right? So it is comparables. So that's why ray optics it fails to explain the propagation of light in case of the single mode fiber. So that time we have to consider the mode optics. In the mode optics, what we have done, we have considered the Maxwell's equations. We have solved the Maxwell's equations with boundary conditions. Basically, we have developed the wave equations. Somewhere I'm writing it here. Any blank? Okay, here you can see what we have considered. I'm telling you, we have developed the wave equations from Maxwell's equations. Maxwell's equations we have seen del cross H, another del cross E, and del dot D, and del dot B. Right. So there the four equations we have considered. Curl of H, curl of electric field, the divergence of electric displacement, and magnetic flux density, electric flux density, right? Displacement. So these things, from this we have developed the wave equations, wave equation, and we have solved the wave equations with the boundary conditions. So tensile components of electric fields are continuous, like these things, like say E2 minus E1 equal to 0, H2 minus like this. This is the boundary. They are the boundary conditions. With the boundary conditions, we have solved the wave equations. What wave equations we have solved? Just a minute. I'm showing wave equations. That is del 2 E upon del T2. That is del 2 E by del 2 del square E minus mu epsilon del 2 E by del T2 that is equal to 0. Similarly for magnetic field also. So these wave equations we have solved with the boundary conditions, right? So to get this one, we have you see actually you are considering this curl of H. We have different components. We have written this, say E R, E phi, H R, H phi in terms of Ez and Hz. All are expressed everything's Ez and Hz, right? Because here a little bit we have modified. That is because here fiber is circular, so we have considered the cylindrical coordinate systems. No, cylindrical coordinate system R phi Z. This is R, this is phi, and this is Z direction. R phi Z cylindrical coordinate systems. So we have expressed all the components in terms of longitudinal components, this Ez and Hz, and from this we have considered the concept of modes. When you consider, you have developed the wave equations for this electric field and magnetic field, and we have seen this, they are not coupling each other. So you can have, because electromagnetic wave theory, so electric and magnetic field will couple each other in the form of pulse that will propagate with a different velocity, right? So that you can have it, more solutions are obtained generally when you consider Ez equal to 0. That times we are considering these TE modes. When Hz equal to 0, we are considering the TM modes. When Ez and Hz both are non-zero, that times we are considering the hybrid modes, He or H, right? They are the hybrid modes. In other waveguides, you cannot see this hybrid mode because other waveguides are hollow waveguide. This fiber is solid. That's why these hybrid modes are existing in case of optical fiber, hybrid modes. In fact, I told you several times, single mode fiber, these hybrid modes, the mode that is propagating it is He11. Of course, this is this you cannot visualize this mode. Actually, it consists of two LP modes, LP01, which are orthogonal. Two LP01 modes which are orthogonal to each other. Right? These are the fundamental modes. This you can see it. Right? The linearly polarized modes. Well, these suffixes, why two suffixes are there? Because you have seen this. These are when you want to solve these equations, there will be 4 parameters will be there: R, phi, omega, t. So 4 parameters will be there, and we have seen this separation of variables. If you consider in terms of R only, then you'll get the Bessel's differential equations, right? And that Bessel's differential equation means solution will be in terms of Bessel function. So Bessel function, we have seen this, they are varying in or oscillatory in nature, right? Because of this oscillatory nature, there will be m roots for a particular value of nu, say J0, J1, like these things, right? So that's why these suffixes will be m nu, right? The two suffixes will be there. And when it is He11, m nu, so new m's. So He11, that is the fundamental mode, right? So the mode concept is coming from these ones, right? And we have seen this bound mode conditions. When you consider, if you analyze these Bessel functions, then we can have the bound mode conditions, that is, into K0 less than equal to beta less than equal to N1 K0. That is the most important conditions for bound modes. Like say total interflexion condition is for the ray optics, but in this case the bound modes, this constant must be satisfied. And the propagation constant beta should be greater than this N2 K0, or should be less than N1 K0, right? So that is the bound mode conditions. And also we have seen this with this mode concept. Actually, your aim is to calculate the value of beta to get the field distributions. So we have seen this. For T modes, you can have it, but for the hybrid modes, it will be much more complicated. Numerically, it will be solved. So once you get the value of beta, then you can have the field distributions. And for He11, it is almost Gaussian in nature. We have seen it Gaussian in nature, modal. And that times in single mode fiber, you have seen it is not the core diameter, rather MFD, mode field diameter, is most important. Means here this what is this one? That is 1 by E square of E0. This one here, it is 1 by E square times E0. right? So that is the mode field diameter. We have seen this, how this mode field diameter can be determined, right? Anyway, many things are there already. Will you tell me exactly what you want to know? So, but these are the basic concepts of the modes, etc. और बोलो, और क्या 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 जानना चाहते हो?
No, sir.
हर्षवर्धन, हाँ?
Yes, sir. I understood, sir.
कुछ भी specific question है तो पूछो, then I can answer it. Any specific questions? Because it's a everything will be there, so it will take longer times to describe in details. Right. I mean, even if you consider the brief, unless I know what is your focal point, it's difficult to answer it. So if you mention any specific point, then I can answer it. Yes. Harbhajan.
No, sir.
Any specific? Okay, then next time we'll see. Any other people are listening? I don't know whether. Let me check whether the sleeping quiz will be there.
Excuse me,
But
sir.
no one is.
What is the
Yeah,
duration of
follow.
this? What is the duration?
Half an hour दिया तुम half an hour बोलो तो half an hour ही दिए हैं.
Okay, yes, sir.
Excuse me, sir.
Yeah,
Sir,
नाम बोलो
we
पहले.
have one request, sir. We are having Samsung online round on today on
That already
5
I've
PM.
that already Harshvardhan is mentioned, but already have posted, and so it's difficult. So you have to miss that one. Otherwise, we miss the quiz or miss this one. Before, if you announce it earlier, then I can consider it.
Sir, it
I could
was
consider, but
announced today only the time.
that is true, but already quiz is there. Quiz exam is during exam period. Exam cannot be postponed, right? That you should mention earlier. Otherwise, I'm sorry for it. Already is posted. I cannot change it. Bolo? Or any other questions? Deep Rishi, you are you want to say
No, sir.
something?
No, sir, I had
Okay.
asked.
Naman, you want to say something? Naman? No. Okay,
sir.
then okay, you see, I'm sorry for I cannot change it because just even if you say yesterday, then also you can change it, but already I have posted it and also I have communicated to other branches also. It's difficult to change. Anyway, it's a half an hour. Anytime you can answer it. 50% will be simply 1 second you can answer it, and 50% some numerical, basic numericals will be there based on this concept, and that you can do it. Okay, then just see it and go through it, and I'm leaving now.
Thank you, sir.
Quiz will be at 6 to 6:30. Okay.